Today we will do an activity, the purpose of which is to verify the thin lens equation. Yesterday you learned what the thin lens equation is. It's the same as the mirror equation. 1 over f is equal to 1 over do plus 1 over di. I told you that it works. Today we're going to do an experiment that shows that I didn't just make that up, and that I'm just not giving you something because it's convenient. I'm giving you something because it actually is true. We're going to verify this equation to show that it's correct, to show that it's valid. Well, how are we going to do this? We're going to set up an experiment that looks something like this. You're going to have a meter stick. The meter stick is going to be sitting on 2 meter stick holders. You can see one of them in this picture, and then one of them is going to be down here somewhere. There is also a converging lens. The converging lens is right here. It's held in place by what we call a lens holder. It clips right onto the meter stick. Right here is a card. That's going to act as our screen. That's going to be held in place by a screen holder. We can attach that to the meter stick as well. Down here we have a candle and a candle holder that attaches to the meter stick. The candle will be our object. We want an object that generates its own light, because that object tends to be brighter than other objects. Somebody might say, well, why don't you just use a pencil or something as our object? It's a little bit safer than using a candle. Pencils reflect light. Pencils should cause an image to be formed on this piece of paper on the screen over there. The problem is the pencil doesn't reflect nearly as much light as the candle produces. So although you might possibly see a bit of an image of the pencil on the card, you wouldn't see nearly as good of an image on the card of the pencil as you would of the candle. So this is going to be our object, this is going to be our converging lens, and this is going to be our screen. We are going to change the position, or we're going to change the object distance and see how the image distance responds to that. We're going to take that data, we're going to do something with it, and then we're going to plot a graph. That graph will tell us whether or not this law, this equation, this lens equation that we learned yesterday is valid. The procedure is written in front of you right now. It's also up on the board here. We set up the optics fence, as I just showed you just a second ago. We determine the focal length of the converging lens. I think we demonstrated this yesterday in class, didn't I? When it focused on a far-off object, and we were able to see the image on that card. We move the card back and forth until we see a good, clear, sharp, focused image of that object on the card. Measure the distance between the lens and that card. That will be our focal length. Write that down. Then you're going to take our object, which is in this case our candle, and we're going to place it at an object distance that's greater than the focal length. So if you find your focal length to be 20 centimeters, then you want your object distance to be at least 23, 24, 25 centimeters. Start there, and then keep making your object distances with progressive trials larger and larger and larger. Place your object a certain distance from the lens that is bigger than the focal length. Then I want you to move the card back and forth until you see a good, clear, sharp, focused image on the card of this object. In other words, you're going to see a candle on the card, or at least the flame of a candle on the card. Measure the distance between the lens and the card. That will be your image distance. Then you're going to do that again 9 more times, so that you have a total of 10 object distances and a total of 10 image distances. That's our data. And it should look something like this, except that you're going to have more of it. What are we going to do with that? Because that's not enough to tell us whether this lens equation is valid or not. We're going to create an analysis table that looks like this: 1 over do, 1 over di. Now, people in my second period class asked me, well, how do we find 1 over do? Don't overlook the obvious. If the value of do is 1, then the value of 1 over do is 1 over 1. It's 1. If the value of do is 2, then the value of 1 over do is 0.5. If the value of DO is 3, then the value of 1 over DO is 0.33, and so on. Do that for DO, do that for DI. Once you have 10 different values for the inverse of DO and the inverse of DI, then you're going to plot a graph. 1 over DI is a function of 1 over DO. Feel free to do this on Excel as well, just like we have the last few activities that we've done. Now, the other activities that we've done, we've gotten a graph that looks like this. This time, you're going to get a graph that looks like this. So it's a little bit odd. What's similar about this from the other activities? It's a straight line. What's different? Well, it slopes downward as opposed to upwards, and it doesn't go through the origin. There's a y-intercept here. That's okay. We can deal with it in the same way as we've dealt with the other graphs that we've seen in other activities. What's the equation for this straight line graph as with any other straight line graph? Y equals mx plus b. What's the y-axis of this graph? Well, it's 1 over di. 1 over di is on the y-axis, so let's sub it in for our y value there. M is the slope. X is our x-axis, which corresponds to, on our graph, 1 over do. On each of these analyses that we've done until this point, we've scratched out b. Why am I not scratching it out in this one? Why am I leaving it there? Why is it important in this one? What does b mean? The y-intercept. Why am I not scratching it out? Good, because it's not 0. There is a y-intercept. And in the other activities that we've done, the y-intercept has been effectively 0. It's not effectively 0 here, so we can't scratch it off. The next thing we do after we've come up with an equation from our graph is to come up with an equation from our data sheet. The equation from our data sheet has to have the same basic form as this one does. So let's look for one on our data sheet. What equation has both 1 over di and 1 over do in it on our data sheet? It's the Lens equation, right? 1 over f is equal to 1 over do plus 1 over di. Now let's rearrange this equation to take the same form as the equation from our graph. 1 over di, let's take the 1 over do over by subtracting. It becomes negative 1 over do plus 1 over f. Now somebody earlier asked me, well, why didn't I say 1 over f minus 1 over do? Is that the same thing? It is. Can anybody suggest to me why I put it in that form as opposed to 1 over di equals 1 over f minus 1 over do? I want the one from our data sheet to look as much as possible like the one from our graph. If I'm saying 1 over di is equal to something times 1 over do from our graph equation, then I want to say 1 over di is equal to something times 1 over do from our data sheet equation. I want to put it in the same order. I don't have to. It's not wrong to change the order of this, but it's easier to see what you're looking for if you put it in the same order. Now let's cross off some things that appear in both. 1 over di appears in both. So let's get rid of it. 1 over do appears in both. So let's get rid of it. What are we left with here? Well, we've got the slope over here. The slope is equal to negative? What does that mean? Well, this term right here, we could say negative 1 times 1 over do. Is that the same thing as what was actually written there? 1 times 1 over do is 1 over do, right? So this is the same thing as saying the slope is equal to neg 1. Regardless of which group you're in today, regardless of which class you're in today, regardless of which lens you used or which object you used or anything about this, the slope of your graph will be negative 1. It doesn't matter what data you use, the slope of your graph will be negative 1. We don't need that number. It's always the same. It's very predictable. It doesn't help us. The slope isn't what we want today. Rather, what we want today is this, the y-intercept. B, the y-intercept, is 1 over f. If the y-intercept is 1 over f, then f is 1 over the y-intercept. So you can go on Microsoft Excel and you can click that display equation on graph and you can get the slope, and it's going to be either 1 or something that's very, very, very close to 1. But what we want to look at when we get that equation from the graph is the y-intercept. Because we're going to take that y-intercept, flip it over, get the focal length. Now, we've already got the focal length. We measured it right here. Right? Your focal length was, what, 20 centimeters or whatever it worked out to be. That's what we're going to call our theoretical value. That's what the focal length should work out to be. This is what we're going to call our actual value. This is what we actually got for the focal length. We're going to compare the theoretical value to the actual value by using the percent difference equation. Actual minus theoretical over theoretical times 100. If that number for percent difference is 10% or less, then we're going to say that the lens equation was verified. If it's a number that's bigger than 10%, then we're going to say the lens equation wasn't verified. How is that enough to tell us that the lens equation is verified or not? Just because we've calculated the focal length and it agrees with the number that we measured early on in the activity. Well, what did we do? What did we assume to get that number? We assumed this equation to be correct. If we made the assumption that that equation is correct, and then the numbers match up, then that equation must have been correct. Hence, if those two numbers match up, we've verified the assumption that we made to get that number. Does that make some sense? So get the focal length by measuring it at the beginning of the activity. Get the focal length by our graph calculations towards the end of the activity. Compare those two numbers. If they're equal or really close to it, then that's enough to tell us that this equation is valid. Our conclusion is it's valid. What do you got to hand in? Well, the problem, which was given to you, I'm not even going to mark the problem, to be honest. What I'm going to mark is the stuff that isn't given to you. The variables, the data, the analysis, which of course includes your analysis table and your graph and the work with showing what the y-intercept represents. Your conclusion, which basically just says, was the thin lens equation verified, and how do you know? And then, of course, your sources of error. Included with your sources of error should be improvements or possible improvements. So there's a little bit more on this one than there has been on the last couple of activities that we've handed in, but we're going to have a few days to do this. It's not going to be due until Monday. Make sense? One more quick little thing that I want to show you, which is kind of just an aside here that helps you to kind of see results when you're seeing results that you want to see, okay? I snapped a couple pictures here, one of an image that's good, one of an image that's not good. I can see light in both cases. I can see light right here, and I can see light right here. Which one is the good image? Diagram 1 or diagram 2? Yeah. Diagram 2 shows me, if you look at it closely, and it's kind of small from where you're sitting, but it's an upside down flame. Diagram 2 shows me a circle of light. Light will always go through the lens. You don't need an image to be formed to see light on the other side of the lens. An image is something that's focused. Diagram 1 has a focused image. Diagram 2 doesn't. So if you see something like you see in picture 2 there, that's not what you're looking for. Okay, you're going to see that lots. Don't stop when you see that and measure some kind of image distance. Okay, when you see the picture in diagram 1 there, stop there, because that's your good, clear, sharp, focused image. Measure the distances then. All right? Let's get out of here, guys.